Well, welcome back. Greetings, everyone. So we're going to follow up on the previous video, and it's a very similar topic. However, notice that we're talking about the same information, same concepts, but in C. So bitwise operations and bit masking in C versus the previous video, which was talking about it in the context of ARM assembly. Okay. Now, I'm not going to go over what the different bitwise operations are. We've already seen that. I want to really start by just mentioning some of the syntax for doing bitwise operations in C. A lot of it is fairly straightforward, right? If just one thing I would kind of point out is if I want to grab a single byte in C, have just stored just a byte in memory, I could make it a character as a data type. A character is 1 byte long. So that's one way of kind of saying, hey, I'm going to have a byte, right? 1 byte of information, okay? So if I want a byte, I could go ahead, I could store it this way. I could set it to a particular integer number, right, to get it to say be 5, okay? I could also do something like this, where I could set a particular variable, if I wanted to make an integer or an unsigned byte to make it, a particular number of bits. I could use OB to make it a binary and set it to 5 that way, right? So I could do just 1, 0, 1, or you could have leading zeros as well. So I could, it depends on how many bits you're going to allocate total, right? If I wanted it to be exactly 1 byte long, an unsigned char is a good way to do that, right? Because if you remember that in the C language, unsigned char or a char is exactly 1 byte long, okay? So here I'm doing it in base 10. Here I'm representing that number in initializing it in binary. I could also do it in hex, right? I could also say, hey, I want to use hex for this, and I'm going to do that with OX, okay? OX to be able to go ahead and initialize it that way, or I should say 0x, right? Whatever I wanted it to be. All right. So here's a way where we're talking about initializing variables in base 10, right? Binary or hex. All right, that's this example here. Okay. When it comes into C in terms of printing things out, we want to remember we've got this these format specifiers, right? We got the format specifiers are going to give us the control of how we print things out. Okay, so here I'm going to use the D for decimal for base 10. Okay, I'm going to print out this. I'm just going to take this byte right here, and I'm going to print it out 3 different ways. Right, I'm going to print it out using this format specifier. Okay, actually I'm going to do it in 2 different ways because we actually don't have a format specifier for binary. But I could do it in base 10, and I could do it in base 16, or aka hexadecimal. Okay, you could also do an octal too if you want. I'm going to kind of skip over that, but we're going to see printing that byte in base 10 or in hexadecimal. I might change the value in a second so that the hex is a little bit more meaningful, because right now we're going to get the same thing back. I'll just show that running. Okay, I forgot to put the new line. Right. This isn't a very interesting number to work with because it's going to look the same in base 10 and in hex. But if I go here and I change this to something like, oops. If I go here and change it to say 11, right, now we're going to see something a little bit more meaningful when we run this, that we see it in base 10, and then we also see it in hexadecimal. Okay, so we've got the control of how we want to initialize in terms of what base the data, and we also have control in how we want to display the information, aka what base. All right, so that's important. That can be very helpful as well. All right, having that level of control. All right, now what we haven't shown yet is, let's take a look. Let's do a couple examples where we have a couple numbers here that we're going to do some bitwise operations on, just so we can see what the different bits are, and how the what the different bitwise operations are in the context of the syntax of C, right? If I wanted to do an OR operation, I've got variable A, variable B, 5 in binary we just saw is this, right? 9 in binary is going to be that, okay? And if I want to OR those values together, right, the inclusive OR would just be a single bar, okay? Now notice there's a bit of a theme in C in terms of how the syntax works. Notice that if I'm doing a logical comparison, something that results in a Boolean value, right? If I wanted to do something like I have A equals 5 or B equals 9, okay? If I was doing that in C, the two vertical bars, both of them together, is resulting in a true false, right? It's a logical operation resulting in a Boolean output. Same with the double equals, Boolean, right? Versus an assignment with a single equals, right? Results in a true false. It's a comparison, okay? The general rule is that if it's a single version of that, that's the bitwise operation, right? It's doing a bitwise OR, okay? It's the same thing if we were going to do, I'm missing the format specifier here. It's the same thing if we were going to do a bitwise AND operation. Okay, it's just a single AND, right? If I wanted to do a bitwise exclusive OR, and you don't have to memorize this. This can all be documented for you to reference. We're going to have the little hat symbol, like the caret symbol for exclusive OR, right? If I want to negate A, I'm going to do the tilde, right? Flips all the bits. Okay. So that's our negation operation or not operation. And then what's really also very common is if we wanted to do some sort of shift, right? If I wanted to shift A to the left by 2 bits, or if I wanted to shift B to the right by, say, 3 bits, these are our shift operators, okay? It's the less than and greater than signs, 2 of them back to back, okay? So that's a quick summary of our bitwise operations in C. Why don't we do one example using bit masking in C to kind of let this sink in? And I'm going to try to do something that's a little bit more realistic, okay? So I'm going to start. Let me delete this so we can look at a new program from scratch, okay? And those bitwise operations, you could look at the table to reference those. You don't have to, it's easy enough to just look them up as long as you know what they mean. Let's take a look at. Let's imagine we have a machine language instruction, okay? So let's have a machine language instruction. And I'm going to put this in as an integer, and I'm going to represent it in hex, okay? So it's instruction in machine language, and I'm going to represent it in hex. I'm going to do 0x, right? And I'm going to initialize. This is going to be, let's do I'm going to run, I have a little assembler that I wrote here that's going to generate the, it's going to generate the machine language ARM instruction for us. If I write in an instruction here, right, let's do something like this, okay, it gives me here the machine code version of that, right? So I'm going to go ahead, I'm going to write this down. That's the machine code version of it in hexadecimal. So we have 8B020065. That's our 32-bit ARM machine code instruction. So I'm going to go ahead, I'm going to initialize this instruction as that, okay? Right. So this instruction is an add, what did I say? Add R5, so it's R3 plus R2, and that's saved in R5. So add R5, R3, R2. It's that instruction. Let's imagine that we want to convert this instruction to be the same exact thing, okay, except I just want to change the instruction to maybe be an OR, an inclusive OR. I want to change this instruction such that the registers are exactly the same, okay? I just want to change the instruction, okay? Just as an example. And we're going to do that using bit masking, okay? Let's kind of reference something we've seen prior, right? We know that both an add, if we look at our documentation here, okay, we know that an add instruction is an R-type instruction, okay? And we also know that an OR instruction is also an R-type instruction, okay? So they're both R-type instructions. That makes things easier for sure, because we're not really messing with the instruction format. Okay, there's no difference in instruction format between the two. And let's just look here and just remember that a R-type instruction, the opcode, remember the opcode defines the instruction. So the registers and everything else is going to stay the same, and the shift amount. Registers and shift amount is going to stay the same. The only thing we care about is these 11 bits for the opcode here. That needs to change, right? We need to change the opcode, all right, from the add instruction to an OR instruction opcode, okay? The first thing I'm going to do is I'm going to use bit masking to zero out these 11 bits, okay? I'm going to use bit masking to zero them out, all right? So let's do that first. Let's define a bit mask. I'm going to define a mask, okay? I'm going to do it in binary. I'm just going to count out 11 bits. That's 8. I'm going to be very careful I don't mess up. That's 8. Okay, that's 11. Okay, so that's 11 bits. Okay. What I want to do though is I want those bits to be in a certain location. Okay? This is 11 bits where the rightmost bits are the 11 bits. Right? So right now, our rightmost bit starts at 0. I don't want that to be at 0. I want that, right? We have our leftmost 11 bits to be from here all the way here, right? As part of the instruction. Like they're kind of running here, right? We want the bit masks to be all the way over to be here for the opcode, right? So I'm going to shift everything over. Okay, I'm going to shift it over by 21. Okay, by 21. Right, so I'm applying the bit mask correctly. I'm just going to shift it over by 21. Right. Now, if I want to zero out, okay, so what I can do, right, is if I want to isolate the opcode, right? If I want to isolate the opcode here, we have to be a little bit careful because effectively we kind of have things right now a bit of reverse, right? Where the goal is we want to do something like this. Let me take a little bit of a blank to just kind of draw this out for you. We have some bits, whatever it is, I'm just going to make up whatever they are. Okay. And this is our original instruction. Okay. And our goal is we want to take the 11 most bits and we actually want to zero them out, while leaving all of this unchanged. Okay. Right now, my mask looks like this. Okay. It would actually make sense to flip this, right? This is the mask. It would make sense to flip the bits here. Okay. Because if we AND this here with this here, okay, we're going to get everything minus the opcode is going to be all 0, right? The opcode will be all 0. So if I go back here to the original code and I just flip all the bits for the mask, okay, what that effectively gives me, right, if you kind of trace that out, that's going to give me the 11 leftmost bits to be all zeros and everything else to be ones. Okay. If I do that, right, and then if I can modify the instruction, okay, this will give me everything minus the opcode. Right, it will have the opcode will be all zeros. And there's multiple ways to do this. This isn't the only way to do it. I'm just kind of illustrating the different operations. Okay. Now we've zeroed out the old opcode. We can insert the new one. Okay, so what effectively these steps did, zeroed out the opcode. 11 leftmost bits, the most significant bits. Okay, now we're going to, for this down here, we're going to actually replace the opcode with the OR opcode. All right, we're going to replace it. All right, and there's, you can do this in less steps. There's smaller ways to do this, but it's a good example of showing the bit manipulations. Okay, you can certainly find ways of doing this in less steps. Okay. So we've zeroed out the opcode, the leftmost bits. Now we're going to replace the opcode. Right. So let's say, well, what is the opcode for the OR instruction? We can look at it two different ways. All right, I could come up to, let's take a look at the documentation here. Let me find it. The OR instruction has an opcode in hex of 550. 550. Okay. Okay. Now, if I want to build a new mask with this, right? Well, we might want to, let's line up the opcode. Right? Why don't we line it up so that those bits are in the proper spot? Right, let's shift them left to the proper amount. It should be 21. Okay. Okay. What we've done, right, just to recap, what we've done is we've got our add instruction, our original instruction, right? It's got multiple pieces. It's got the opcode, right? We have a shift amount. Okay, we have some registers. What we did is we zeroed out all the opcode. Okay. We then defined a new opcode. We took the OR opcode, which is 550 in hex. Okay. This is actually 12 bits. We're not going to use this leftmost one. Okay. 550 in hex. We line that up here. All right. And what we're going to do is we're going to now bitwise AND these together so that we can have a new OR instruction such that we've changed this from an add to an OR, and all of these registers are going to stay the same. Okay? Because we know this OR instruction, everything down here is all zeros. Okay. Actually, I should be careful. This is not a bitwise AND, it's an OR, right? We have zeros all here and here, and we want to combine these together. Okay, so it's an OR. It's not an AND. It's an OR instruction. Okay, bitwise OR to combine them together. All right. So let's combine them now, right? So our new instruction, our OR instruction, is going to be instruction bitwised, and then our one with the OR opcode. We can print it in hex. All right. Let's run this. Okay. We get this instruction here, right? And we can confirm that that makes sense, that it's the same thing that we've seen prior. It does look right just by scanning it, if you're able to see this. Notice I can tell right off the bat that we didn't change any of this part of the instruction, which was our goal. We only wanted to change the opcode, right? That looks correct, that we only changed the opcode. Okay, we can verify. We can come here, we can run this. We can say, hey, let's run an OR. Okay, oh, and actually I can't test it in here because I never built this assembler to work on that instruction. But that looks right. Let's just verify. Let's do it by hand. AA0 at the end for the opcode. AA0. Let's go ahead and just do it out just to make sure that everything worked correctly. Okay. So we look at the beginning part of that instruction. AA0. Okay, A is 10, right? 8. This should be that. Right? 8 plus 2. 10 followed by zeros. Let's make sure it's what we expect for the opcode, right? We said that the opcode, we saw just a moment ago that the OR opcode was 550 in hex, okay, which is 101, right? This is correct because we want to remember that's 12 bits. We lose this last bit here, so it's that. Okay, that looks like it matches up here, right? 101, 0, 1, 0, 1, the rest 0. So our code was correct. Okay. All right, so that was the quick rundown. I mean, I'd expect that people need to pause and maybe watch this multiple times to let it fully sink in. But at this point, you've seen these bitwise operations and bit masking, both from an assembly language perspective as well as doing a longer, more detail-oriented example in C. Right? So watch it as many times as you need to let it sink in. Otherwise, we'll follow up in class, and I'll talk to you in class.